Hello everyone, welcome back to Z Physics. Today we're going to be revising the whole of the wave section of the A Level Physics syllabus. Once again, I'm going to be following the OCR Physics A specification. However, the physics is applicable to all exam boards. So let's get started. Now, the first question that we need to answer is, what is a progressive wave? Remember, progressive wave transfers energy from one place to another. They can be split into two categories, a transverse wave and a longitudinal wave. In a transverse wave, the particles oscillate perpendicular to the direction of propagation of the wave, or the direction of energy transfer, you could also say. And examples of transverse waves include water waves, EM waves, and many others. In a longitudinal wave, the particles oscillate perpendicular to the direction of the propagation of the wave or the direction of energy transfer. Typical examples include sound waves and P waves in earthquakes. Okay guys, now time to look at some wave properties. First off, the displacement. Now the displacement is the distance from a point in the wave to the equilibrium. For instance, I've drawn them over here in gray. This point right here is going to have the following displacement, whereas this point here will have the following displacement, and any point on the wave will have some distance from the equilibrium position. The maximum displacement from a point of the wave to the equilibrium position is known as the amplitude, which I've drawn here in blue. The wavelength, on the other hand, is the minimum distance between 2 points in phase. This could be the peak-to-peak distance, for instance, or it could be the trough-to-trough distance, or the distance between any 2 points in phase. For instance, this one over here and another one right over there. The time period, on the other hand, is the time taken for one complete oscillation. The frequency tends to be the number of cycles per unit time, and the hertz, the unit for frequency, is the number of cycles per second. Those two quantities, time period and frequency, are interlinked by the famous equation that the time period is equal to 1 over the frequency, and of course the frequency is 1 over the time period. As I mentioned, your time period is measured in seconds, whereas your frequency is measured in hertz, which fundamentally is seconds to the power of -1. The wave speed is defined as the distance traveled by the wave per unit time. Because of that, we can write down that the speed of the wave v is equal to distance over time. Now for one complete cycle, so for one cycle, the distance traveled by the wave is actually equal to the wavelength, and the time that's elapsed during that one complete cycle will be equal to the time period. Algebraically, we can write the following equation as lambda times 1 over the time period. But hang on a minute. Remember, we said that 1 over the time period is actually the frequency. So if we were to plug this in here, what we're actually going to get is that speed is equal to frequency times the wavelength. And this is the famous wave equation in which v is the speed of the wave, f is the frequency, and lambda is the wavelength. Right, on to phase difference next. So phase difference describes how far out of sync 2 points on a wave are. It can generally be described by the equation that phase difference is equal to the distance between those 2 points on the wave over the wavelength times 360 degrees. We can apply this equation to a little sample problem over here, in which we have two waves that have peaks separated by 60 centimeters, and we're given that the wavelength is 80 centimeters. Find their phase difference. So in this case, the phase difference, which is often given this symbol phi, will be equal to x over lambda times 360 degrees. So our x in this case is equal to 60 centimeters. Our wavelength, this really should say lambda. Maybe I should make this a little bit more legible like this. So our wavelength is 80 centimeters. The centimeters are just going to cancel out, so I could write in the factor of 10 to the power of -2, but that will just cancel out. So I'm not going to write it, and I'm going to just multiply by 360 degrees. And if we were to just put this into a calculator, we are going to get 260 70 degrees. So the phase difference between those two waves is 270 degrees. A very useful rule of thumb to remember is that if two waves differ by 180 degrees, that they're going to be differing by half a wavelength, because this fraction over here will be a half. If they differ by half a wavelength, a peak will be meeting a trough. And if we see a wave pattern in which one wave, the peak of one wave meets the trough of another wave, such as these two waves over here, then we instantly know that the phase difference phi in this case is going to be 180 degrees. Right guys, let's revise oscilloscopes next. In all of the oscilloscopes, all of the squares always have a side of 1 centimeter. Each horizontal space actually represents a time interval. So in a way, on the x-axis we have time. Each vertical space, or the height of the signal, represents voltage. We could use this graph, for instance, to find the frequency and the amplitude of the following signal. If the oscilloscope is set to 1 milliseconds per centimeter and 2 volts per centimeter. Now, what does that mean? If the setting is 1 milliseconds per centimeter, this means that each square represents 1 millisecond. So from here to here is 1 millisecond, and from here to there is 1 millisecond, and 1 millisecond as well. The length of this signal is 4 squares, therefore the time period will be equal to 4 milliseconds. The height of the signal, which is just 1 square, like so, and we can directly see the amplitude if that's the case, because the length of 1 square is 1 centimeter and it's 2 volts per centimeter, so therefore the amplitude, I can just say over here that the amplitude is equal to 2 volts. Now, given the time period, let's work out the frequency. Our frequency will of course be 1 over the time period, which will be equal to 1 over 4 times 10 to the power of minus 3. And if we were to just put that quickly into a calculator, or using a bit of mental maths, we can work out the frequency is 250 Hertz. So let's have a look at 3 main properties of waves. The first one is reflection. This occurs when a wave changes its direction and boundary while remaining in the original boundary. For instance, if we have a ray of light which essentially strikes this surface over here and then it reflects, it will remain in the original boundary. The condition to satisfy in this case is that the angle of incidence is equal to the angle of reflection. So let's write this in. Our angle of incidence is equal to the angle of reflection. Note that the angles are measured from the normal. Refraction, on the other hand, occurs when a wave changes its direction and speed as it moves from one medium to another. Quite typically with EM radiation, the frequency will remain constant, but the speed and the wavelength of the wave will change. We could also have diffraction, which is the spreading of a wave as it passes through a gap or around an obstacle. In order for this to occur, the gap size needs to be similar to the wavelength, as it is in this case. Now let's talk about intensity. Intensity is defined as the power that's been transmitted per unit area. The equation for intensity is that intensity is power divided by the cross-sectional area. The units of intensity are going to be watts per square meter, so watts m to the power of minus 2. Intensity varies with distance in the following way. Imagine that we have a point source. This could be a speaker, it could be a light bulb. The intensity will be spreading out, or the intensity of the wave will be spreading out like a sphere around this object. Because the surface area of a sphere is pi, or 4 pi r squared, we could rewrite the following equation as power divided by 4 pi r squared, where this is the surface area of a sphere. In other words, anywhere around the surface area of this sphere, the intensity will be the same. If I was to go a little bit further, the intensity is going to be lower. If I was to go in a little bit closer, the intensity will be higher. So this will allow us to calculate for instance, the power that's been transmitted from a source of intensity I at a distance r. Or we could calculate the intensity of the source if we had the power and the distance to the source. It's really important to note that in this case, the distance really is represented by the radius of the sphere. So this r over there is the distance from us to the source. How does intensity depend on amplitude? So this is really, really important, that the fact that intensity is proportional to the amplitude squared. Let me just write this as intensity is proportional to the amplitude squared. Mathematically, we can often express this as the intensity being proportional to the amplitude squared with some constant of proportionality k that we use to calculate using proportionality problems. So in practice, if our amplitude increases, let's say twice, because our amplitude is squared, if we square 2a squared, well, this will give us a factor of 4a squared. So if we increase the amplitude twice, our intensity will increase 4 times. We could do the reverse as well, so we could also say that the relationship between the amplitude and the intensity is as follows, because we can also say that our amplitude, in a way, is proportional to the square root of the intensity. In the past, I've done some very, very detailed videos on those two equations. I will provide a link into the description in which I do quite a lot of examples in finding the intensity or finding the amplitude by manipulating this relationship that the intensity is proportional to the amplitude squared. So if you would like some more or some extra practice on this, please have a look into the description of this video. So let's have a look at some properties of electromagnetic waves. Number one, they can travel through a vacuum. This is how the sun's energy is transferred through the vacuum of space to reach the Earth. They also travel at the speed of light, which is 3.0 times 10 to the 8 meters per second. Electromagnetic waves are transverse waves with oscillating EM fields. They normally have two components. One is the electric field, the other one is the magnetic field, but we study that in more detail in the second year. The EM spectrum consists of the following types of EM radiation. At the longest wavelengths, we have radio waves, which are essentially longer than 10 centimeters to very long indeed. Microwaves tend to be of the order of a few centimeters, or 10 to the power of -1 to about 10 to the power of -3 meters. All of these, by the way, are in meters. After that, we get infrared radiation, which goes from 10 to the power of -3 to about 7 times 10 to the power of -7 meters. Visible, or the spectrum of light that we can see, extends between 7 times 10 to the power of -7 and 4 times 10 to the power of -7. Personally, I always remember that at approximately 700 nanometers to about 400 nanometers. Ultraviolet goes after that with a range between 4 times 10 to the power of -7 to 10 to the power of -8. X-rays, -8 to -10, and gamma rays, 10 to the power of -10, and considerably smaller. I believe one of the smallest ones that has been observed has been about 10 to the power of -16 meters. Let's revise the polarization of waves, and in particular of EM waves. A wave is defined to be plane polarized if the particles or the electromagnetic fields are oscillating in a single plane. And this here is a property of transverse waves. Unpolarized light tends to be represented by this symbol, so we can say that the light is oscillating a little bit in the vertical direction and a little bit in the horizontal direction. In practice, unpolarized light tends to be oscillating virtually in all directions, so it tends to be oscillating a little bit along here, and a little bit along here, and along there as well, etc. If we had vertically polarized light, we'll just represent it by this double arrow. If we had a horizontally polarized light, we'll just represent it by this horizontal arrow. Very importantly, longitudinal waves cannot be polarized as their oscillations are parallel to the direction of energy transfer. Let's just change that. This should really say oscillations like that. But as I said, longitudinal waves cannot be polarized. Their oscillations are parallel to the direction of energy transfer. And because of that, they're already limited to a single plane. We can use polarizing filters, and you can have a look at my terrible drawing just over here. Let's make it a little bit more clear. So what I'm going to do is I'm going to highlight the actual polarizing filters in green. That will give it a little bit of color, like so. Look at that, like a piece of modern art. Now, in this case, we have some light which is coming in unpolarized. So it has a vertical component and it has a horizontal component. When it passes through this polarizing filter, because you can see that we can only let through vertically polarized light, in other words, it will absorb the horizontal component, and the light which leaves is now vertically polarized. If we were to place another filter on this side, then this polarizing filter will absorb the vertical component and only horizontally polarized light can go through. There is none on this side, therefore all of the light is going to be blocked. Notice that that filter here and that filter here are at 90 degrees. So whereas one filter is essentially vertical like that, let me just draw it a little bit better. The perspective is not quite right in my work of art over here. The filter, the second filter is horizontal like so. So, time to revise the refractive index of a substance. The refractive index is defined as the ratio of the speed of light in a vacuum to the speed of light in that particular substance. Mathematically, the refractive index N is C over V, where C is the speed of light in a vacuum and V is the speed of light in that particular substance. Because it's speed over speed, overall it has no units. Let's do a little example. The refractive index of diamond is 2.4. Find the speed of light in diamond. It's quite an extreme example, but because n is equal to c over v and n is 2.4, which is really high, the speed of light in diamond will be quite low. So let's rearrange this equation. So we're looking for v. I'm going to write that v will be equal to c over n. C is the speed of light, so that's just 3.0 times 10 to the 8 meters per second. We're going to be dividing that by 2.4, plugging this into a calculator. We're going to get approximately 1.25 times 10 to the 8 meters per second. Notice that in this example, the speed of light has changed because of the wave equation and the fact that v is equal to f lambda. Notice that v has dropped, which also means that the wavelength has dropped. As we mentioned previously, the frequency remains constant during refraction. Let's have a deeper look into refraction. If a wave is going to a medium with a higher refractive index, for instance, if we are going from air, so let's say air, and typically we just assume that the refractive index of air is 1. And as a matter of fact, it's just a tiny bit higher than 1. I believe it's 1.0006 or so, but in the exam, we just assume that the refractive index of air is just 1 to glass. That is a material with a higher refractive index. The light ray is going to bend towards the normal. And we can see this, for to trace this ray, we can see that it's bending towards the normal. On the other hand, if a medium or if a material is going to a medium with a lower refractive index, so for instance this ray over here is now leaving the glass block, it will bend away from the normal as shown here. Check. So how much does a light ray actually bend towards the normal by? By what angle? How could we determine this angle? The way we're going to calculate this is using Snell's law. Let's have a look at this example. We have a light ray which is traveling from air to glass of refractive index 1.5. The angle of incidence is 30 degrees. Calculate the angle of refraction. Snell's law is actually given in our formula booklet, and that is that n sine theta is equal to a constant. Remember, if a quantity is given to be a constant, this means that we can write this down as n sine theta 1 is equal to n2 sine theta 2. In this equation, n1 is your original refractive index, n2 is the refractive index that you're traveling to, theta 1 is your angle of incidence, and theta 2 is your angle of refraction. So in this case, n1 is air because we're traveling from air to glass, so that's just going to be 1 times sine of the angle of incidence, so that's going to be sine of 30 degrees, and that's going to equal to n2, which is 1.5, times sine of theta 2, which is what we're looking for. That's our angle of refraction. So sine theta 2, let's quickly rearrange for sine of theta 2, and sine of theta 2 will be equal to sine of 30 divided by 1.5. Just using some simple trigonometry, we can find the angle by saying that the angle of refraction is equal to the inverse sine of 30 over 1.5. I'm going to carefully put this into a scientific calculator, so sine of 30 over 1.5, and if we do that, we're going to get about 19.5 degrees. So using standard laboratory equipment, we could also measure the refractive index of a material, or at least do an experiment to determine it. How could we do that? First off, we're going to place a ray box on top of a piece of paper, and we're going to vary the angle of incidence, theta 1. We're going to be measuring the angle of refraction, theta 2. In other words, we're going to just place the block on top of a sheet, and then we're going to be firing a ray of light at various different angles, theta. We're going to be varying this angle and measuring the angle of refraction like so. Probably the easiest way to measure these is to mark them on the piece of paper and then use a protractor. As always, we're going to take multiple measurements and take an average. After we have measured the angles, we're also going to calculate the sines of the two angles, and we're going to plot a graph of sine theta 1, which is the angle of incidence, against sine theta 2, which is the angle of refraction. We're going to draw a line of best fit, and let's do the y equals mx plus c analysis. Remember, n1 sine theta 1 is equal to n2 sine theta 2. This is just Snell's law, and n1 is just equal to 1. Because of that, sine theta 1 is equal to n2 sine theta 2, and I've added a little plus 0 like so. Right underneath I've written y is equal to mx plus c, and if sine of theta 1, or the angle of incidence, the sine of the angle of incidence, is on the y-axis, if the sine of the angle of refraction is on the x-axis, our gradient is n2, which is the refractive index of the block. Now, in some very special circumstances, we can get a really interesting phenomenon which is known as total internal reflection. In order for this to occur, our initial refractive index, let's say that this is n1, has to be higher than our second refractive index, which is N2. For instance, if this is glass or a diamond or something like that that goes into air, which has a lower refractive index. Beyond a certain angle, all of the ray can get trapped inside of the block. You can kind of think of this, if you're varying the angle of incidence, this ray is going to get lower and lower and lower and lower and lower, and eventually it will become trapped. It will be fully parallel within here. Let me just draw that perhaps with a different color along here. Now when that happens, the angle to the normal is actually 90 degrees, and that will correspond to essentially a different angle of incidence. Question is, what is that angle of incidence? What is the critical angle? Let's derive a formula for the critical angle beyond which we get total internal reflection. I'm going to start off with Snell's law, which is that n sine theta is equal to a constant. Remember, this means that n1 sine theta 1 is equal to n2 sine theta 2. In this case, theta 2 is 90 degrees, as we can see. So I'm going to write that n1 sine theta 1 is equal to n2 times the sine of 90 degrees. Let's make it even simpler. So let's say that n2 is just air, so this will have a refractive index of 1. If that's the case, n1 times sine theta 1 will be equal to 1 times sine of 90. Well, n2 is just 1 and sine of 90 is also 1. So this whole right hand side of the equation is actually equal to 1, which would mean that our theta 1, or let's say sine of theta 1, will be equal to 1 over that initial refractive index. Let's just call it n rather than n1, and let's call our angle the critical angle. So rather than theta 1, I'm just going to give it a special name, which is the critical angle C. And this here is an equation that we can use to determine the critical angle. Beyond this angle, the ray gets essentially trapped within that medium. Of course, the critical angle itself is going to be determined by the inverse sine of 1 over the refractive index. So when refraction actually occurs, in the case when the original medium has a higher refractive index, if we're below the critical angle, normal refraction is just going to occur. If we are at the critical angle, so let me just say that our angle of incidence is equal to the critical angle, then the ray is essentially trapped at the boundary because this angle here to the normal is 90 degrees. If we go beyond that, over here, and let's say that theta 1 is higher than the critical angle, once again the ray is essentially totally internally reflected. So if we're over here, there's absolutely no sign of the ray, and an object when viewed on this side will actually be invisible. So this is really, really interesting. Okay, folks, this was actually the last bit of waves that I wanted to cover today. We still have a few more bits, but I've actually made separate videos for those. So if you would like to finish the specification, cover everything on waves, please have a look at my video on superposition, Young's double slit, and phase difference, etc. And also have a look at my video on stationary waves. Once again, thank you very much for watching. Good luck in any upcoming exams, and I'll see you guys in the next video.